All right, so we're going to start off with this. If we lived in a perfect world, wouldn't that be nice? We've been doing all these stoichiometric calculations, so you can figure out how much sodium nitrate you can make from sodium hydroxide and calcium nitrate, or anything else. Now, the catch, you knew there'd be a catch. The catch is that we don't live in a perfect world. So we can do all these calculations and say, oh, we should be able to produce this many grams of sodium hydroxide or sodium nitrate or whatever. But in the real world, things don't always react fully. So not all reactions always run all the way. And it might be that maybe it needed to be stirred more, or maybe it needed more heat, or there was some kind of contaminant in the vessel that didn't allow it to run fully. So in the real world, often reactants don't actually get fully used up, and often we don't really truly make all the product we thought we should. But when we do our calculations, we're assuming that everything is perfect. La 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 la, it's a perfect world, it's a perfect world. Everything happens just the way it's supposed to. It doesn't really. That's all I want you to understand, that there is usually a difference between what we say we can make and what we can actually make. If you go on to take quantitative analysis, which is just heavy-duty stoichiometry for 16 weeks at the college level, you do all your calculations, and then you go to the lab and you attempt to get the actual ideal full amount of what you said you could produce. It's challenging. It doesn't happen a lot. And you, in a good quant lab, you keep running the lab until you get down to like 1% error or less. So lots of careful measurement and lots of making sure everything goes perfectly. Now, that said, knowing that we're not living in an ideal world, but we pretend we are, let's talk a little bit about reaction. If we went back to your what do you know question, one of the questions was, when does a reaction stop? And 2 people out of all the classes said, when something gets used up? Yeah, that's exactly it. When you're out of one thing, the reaction can't go any further. So the example I'll give you is if you're making chocolate chip cookies, and you've got all the flour and the sugar and the chocolate chips and the vanilla and the butter, and it calls for 3 eggs, and you only have, or you wanted to make a double batch. It calls for 3 eggs. You have 5 eggs. Can you make a double batch? No. What's going to limit how many cookies you can make? Your eggs. So, and speaking of that, in this chapter, there is a chocolate chip cookie lab. We can't do it this year because of whatever's happening over there. But the recipe is really a good one. Mrs. Dolan's actually copied it from the chemistry book. It's an excellent chocolate chip cookie recipe. So if you're looking for a good chocolate chip recipe, the one in your chemistry book in Chapter 9 is quite nice. Okay, so the limiting reactant or reagent, it gets called either, is just what you run out of. Well, if you run out of one thing, what happens to the other thing? If you run out of one, do you use up all of the other one? No. So we have something that's left over. And that, my friends, is called an excess reactant. So this is the chapter where we do soap, and I assume I am anticipating right now that we will do soap just when we come back from OGT week. Like, I'll probably give you the pre-lab calculations during OGT week. I probably won't see you much that week. We don't know yet. Has anybody here ever made soap? Okay. So what goes into soap?
Some sort of fat, animal fat is what we use.
Any kind of fat.
Any kind of fat. My mother buys these kind of kits, and I don't know what's exactly in the
Okay. So that's a little bit different. If you're making soap from scratch, sort of the old-fashioned way, which is what we're going to do in here, there are 2 ingredients that go into soap. There is sodium hydroxide, NaOH, and there's fat. And this can be lard, it can be beef tallow, it can be Crisco, it can be olive oil, it can be coconut oil, it can be soybean oil. You could break into a liposuction clinic and steal human fat and render it, if anybody's seen that movie. Okay, so any kind of fat and soap, and you get 2 products out of this. You get soap, and soap is actually a chemical compound. When you get your pre-lab calculations, you'll see a molecule of soap. And you get glycerin, which I can never spell right the first time. So you've got sodium hydroxide and you've got fat. Now, have any of you ever rubbed fat on your skin? Bet you have. Have you ever put cream on your skin? Yeah, most creams are a fat base. Your skin, don't forget, you are all fatty water bags. Have I called you fatty water bags before? Aw, my little fatty water bags. So that's all you are. You're a bunch of little tiny bags that we call cells. Inside those cells is water. Those cells, those little bags, are made of a ring of fatty molecules. They're called phospholipids, and that's what makes up the boundary of your cell. So little bags made up of fat that contain water. So you are all little fatty water bags. That's all you are. I mean, you're lovely, nice fatty water bags. It's all good. We're all fatty water bags. Your skin likes some fat. If you have leather boots, you have to grease them. You have to grease your skin, too. Your skin produces greasing agents. It produces oils to keep itself moist. This time of year, we tend to dry out a little bit, and a lot of us need some extra fat on our skin. And so, you get cream, you get moisturizer, you get whatever. We're slathering coconut oil all over my daughter every day because she's covered in eczema, because it's dry. So, is it okay to rub fat on your skin? Yeah, it's good. It's good for you. You're a fatty water bag. It's fine. What's sodium hydroxide? We'll draw a smiley face for fat. We used it in our lab where we had the copper nitrate solution, and then you put a little bit of sodium hydroxide in with the copper nitrate, and you immediately got a chemical response. Yeah, it's incredibly corrosive. Okay, so sodium hydroxide. Well, it's what drain cleaner is mostly made of. So when you get a nice clog in the drain, you've got some fat, some hair, last week's pork chop bone, shreds of rotten green beans, whatever else got stuck down there, and it's all clogging the drain. You dump sodium hydroxide in on top of it, and it'll burn right through that puppy. Yeah, it's corrosive. It'll burn holes in all kinds of stuff. Anybody want to put sodium hydroxide on their skin? No. This is a bad idea. This is a very, very bad idea. Very bad. You don't want sodium hydroxide on your skin. Well, now, when we make soap, we're going to run out of one of these two ingredients first. And whichever one we don't run out of, we're going to have a little bit of extra left in, and it will remain in that bar of soap that you produce. If you had to pick one of these two ingredients that you would prefer to have trace amounts remaining of in your soap, which would you pick? I'd pick the fat if I were you. Yeah. So when we do the stoichiometry to make soap, we're going to calculate it so that we have excess fat in our soap. And as a matter of fact, soaps that are sold as moisturizing soaps tend to have, guess what? Excess fat, or even sometimes fat added back to them after production, because that moisturizes the skin. Okay? Now, I will tell you this. My grandmother made soap for many, many years. My grandma was a little farm lady. She had finished high school, but that was it. She was the first in her family to finish high school. She certainly didn't know, she had never taken chemistry. She certainly wouldn't have known what stoichiometry was if you told her. And Grandma never measured anything. Every time Grandma got a big batch of lard, somebody butchered or something, we'd make soap. And she'd go to the hardware store and she'd buy a can of Red Devil lye, because you used to be able to just buy powdered lye on the shelf. They don't do that anymore, I think because it's a reagent in making meth, maybe. So you can't just buy lye on the store shelf anymore. And it's dangerous, but, lots of things are dangerous. And, we'd go outside and she'd mix up the lye in the water, and then she'd heat up the fat, and then we'd mix it all together, and she'd stir it and stir it and stir it, and, she'd kind of like, yeah, that looks about right. And some batches came out a little different than others. And some batches Grandma would say, oh, that's a strong soap. Guess what was probably the excess reagent in those batches that Grandma said was real strong? a little bit of sodium hydroxide left over. And those she would actually typically put down by the washing machine, and she would use them on Grandpa's work clothes. Because it worked. But you don't want to put it on your face. And then she'd every now and then get a batch that she thought was especially fine. You know, she would say, oh, that's a fine batch. That's a very nice batch. And those would go up to the bathroom for hand washing and stuff. So when we make soap, you are going to do very careful calculations to ensure that fat is your excess reagent. Okay, so I think you understand this conceptually, yes? This seems totally reasonable conceptually. So you know that now, what do we have to do? Put math to it! Yay! I hear an overwhelming, resounding cheer. All right, so you have a reaction here, and the way most limiting and excess problems start is with a statement such as this. Given 150 grams each of silver nitrate and magnesium chloride, which is limiting, which is excess, and how much excess remains? Okay, so to do this, the thing to remember is that you can run a ratio between any two things in this equation. And here you're comparing the two reactants, so you want to run your ratio between the two reactants. Does it matter which one you start with? No. I tend to just start with whatever's first. So I'm going to start with my silver nitrate, and I'm going to start with my given like I always do. Okay, so I've got 150 grams of silver nitrate, and I'm going mass to mass here. I want to know what mass of magnesium chloride this can react with fully. So I'm going to have to get into moles. Okay, so at this point we've gone from our given in grams, and we would now be in moles of silver nitrate. So now we're ready to do a mole ratio between the two reactants. And in this case, we know that for every 2 moles of silver nitrate that we react, we can react 1 mole of magnesium chloride. Now we've climbed down through the valley of the moles. We just got to get back up to the highlands of mass. Okay, we got a number. We got a number yet? Okay, so we've got a raw answer. Awesome. 42.0340 grams of magnesium chloride. Good. What does that mean? So I'll tell you the honest truth. All these years of doing chemistry, and I screw this up, at least the first couple times I do it, unless I write a sentence. But over the years, I've figured out fewer ways to screw it up. So I have a tool for you, a technique, as it were. Blank could react blank, but we have blank. So we will A, run out, B, have blank left over. Okay, this is real simple and formulaic. That first space is whatever you started your factor label with. So in this case, it's going to be 150 grams of silver nitrate. And I'm being sloppy about my sig figs as I write it in because I'm running out of room up here. The second space is the answer you got for your factor label. So in this case, it's going to be 42.0, etc. grams magnesium chloride. But we have, and for that third space, we have to go back to the given amount of this thing. So this is 150 grams of magnesium chloride. So then we need to look at this and figure out if we're going to run out or not. If 3 is smaller than 2, we run out. Okay? If we have less than we could use, we run out. If 3 is bigger than 2, then we have leftover. And the number that goes in that space is just the amount we have minus the amount we could use. So in this case, it would be 150 minus our 42.0 blah, blah, blah. How much do we have left over? Okay, so when we subtract our 42 point etc. from the 150, we're left with, the raw answer is 107.9659, etc. We have 4 sig figs, and it's 107.96, so this becomes 108.0 grams of magnesium chloride left over. Now we got lucky here, and the very first factor label we did told us what we needed to know, which in a perfect world, if everything's working in your favor, you end up answering all your questions with one factor label. It doesn't always work out that way. So, I've got a practice sheet for you. We'll walk through number 2 together on the practice sheet that you picked up today as you came in. And then I'll let you guys work, and I'll kind of circulate and offer assistance where I can. Okay, so we have a reaction, and we have our 2 givens, and we want to know which is limiting, which is excess, how much remains. So we're going to start all of these the same way. Pick a reagent and start a factor label. And my habit, as I said, is to just start with the first one, so I'm going to start with my calcium carbonate. 100 grams calcium carbonate. Okay, so I did go ahead and make note of my molar masses. It's really handy to do that for all your reagents when you start these, because that way you've got them. So I know that 100.09 grams of calcium carbonate is 1 mole of calcium carbonate. I'm ready to put in my mole ratio, and I've got 2 moles of iron phosphate reacting for every 3 moles of calcium carbonate. And now I'm ready to go back into grams of iron phosphate. Okay. What do you get for a raw answer? Okay, so the answer we get is 100.46 grams of iron phosphate. What do we need to do with that? I'd write a sentence. I would write a sentence. Our sentence ready, and our first spot is our given. 100 grams of calcium carbonate could react 100.456 etc. grams of iron 3 phosphate, but we have to look back up to our given. But we have 45 grams of iron phosphate. So, do we run out or do we have leftover? What we could use is greater than what we have. I need 6 eggs, but I only have 3. We're going to run out. So we now know what our limiting reactant is. Which one's our limiting? Iron phosphate, iron 3 phosphate. This is our limit because we're going to run out of it. When the 45 grams of iron phosphate is used up, the reaction stops. Okay, well, awesome. We figured out which one was our limiting. What do we still need to do? We know which one is excess. If one's limiting, the other's excess. But what do we have to do with that? We want to find out how much of calcium carbonate is going to be left over when the reaction is done. We have to do another factor label. Okay? If the first answer you get gives you your limiting, you're going to have to do another factor label. Okay, so since we found our limiting first, now to find our excess, we need to figure out how much will be left. So we're going to start another factor label, but we're going to start it with our limiting, because that's all that we have. So we're going to start with our 45 grams of iron 3 phosphate. Okay, so we have a completed factor label. We've put in our given of our limiting. We've put in our molar mass conversion for the iron phosphate, a mole ratio between the iron phosphate and the calcium carbonate, and a mole conversion between the moles of calcium carbonate into grams of calcium carbonate. So as soon as we've got a raw number, so we have a raw number, 44.7956 grams of calcium carbonate. If we write our sentence again, we're going to plug stuff into that sentence. That is indecipherable. 45 grams of iron phosphate. A little bit better. Could react we'll call it 44.8 grams of calcium carbonate, but we have 100 grams of calcium carbonate. So we're going to have 100 minus 44.79, etc., or 55.204, etc., grams of calcium carbonate left. So if we actually only have 2 sig figs for this, so it would be 55 grams of calcium carbonate left. See how to use the sentence to make sense of the numbers? Okay, the practice sheet you've got, and the paper that Skylar's going to hand you is just a big blow-up of that sentence. You'll use that on your FIP quiz tomorrow. So practice these today, get a good night's sleep, and then we'll quiz tomorrow.